Everybody of us know that there are three major contributors of embryo creation. The first one is spermatozoon, bringing the half of chromosomes where centriole missing in the oocytes and triggering fertilization. The second one, oocyte, which is a major biological contributor of oocyte embryo creation. But we have to consider also the third one, in vitro conditions, including ICSI procedure, which is the ultimate and natural intervention. However, it's clear that without ICSI, the treatment of infertility would be substantially less effective. Therefore, if ICSI is used, we have to minimize potential negative effects of it. And the first and essential condition for a successful ICSI is to inject the oocytes in their real mature state. But the question which I am opening now is if our oocyte maturity evaluation by conventional microscopy is correct. So let's go to clarify it by polarized microscopy, which can reveal the stages of meiosis in much more details by intravital detection of the spindle. Using conventional microscopy, we can distinguish three basic stages of maturity: GV oocytes with a distinct germinal vesicle, M1 oocytes having no polar bodies, and M2 oocytes with extruded first polar body, which are generally considered as mature oocytes and ready for fertilization. However, under polarized microscopy, we can see a bit different pictures. Why GV remain GV, but in so-called metaphase 1 oocytes without visible first polar body, we can find metaphase, anaphase, and early telophase oocytes. And in reality, metaphase 1 oocytes are very, very rare. After analyzing more than 800 oocytes, we found M1 oocytes only in 2 cases. But this is not so surprising because metaphase 1 oocytes occur after GV breakdown, what takes about 25 hours after meiosis resumption, prompted by trigger, while the oocyte function is performed at least 36 after the trigger. This is why the absolute majority of oocytes without first polar body at the time of oocyte function are at anaphase or early telophase 1. Now we should explain what is the difference between metaphase, anaphase, and early telophase oocytes. In the M1 oocytes, the spindle is localized centrally corresponding to the previous position of GV, and the chromosomes are still in the form of homolog pairs. During anaphase, the spindle moves to the periphery of the oocytes and the chromosomes are already segregated. And the position of the spindle and segregation of chromosomes is a crucial difference between metaphase and anaphase oocytes. In early telophase, we can find the first signs of cytokinesis as very subtle protrusions of the oloana. Taken together, we can conclude that so-called M1 oocytes are in fact at anaphase or early telophase 1, and real M1 oocytes are very, very rare. And now you may have a question, why do we need to distinguish it? The answer is very simple. It's about knowledge. Because in embryology, as well as in our life, everything is about the timing. The cells are developing in cell cycles, which are very specific before and after fertilization, and therefore the understanding of cell cycles is a basic knowledge of embryology. The timing of embryo development is better known from time-lapse data, but the oocyte maturation is rather overlooked. This is why we should know it, and therefore it doesn't matter if we call these stages M1 or A1 or early telophase. It's much more important that we know what's behind it and how to manage it. Now let's go back to the oocytes, because even in so-called M2 oocytes, we can see the different pictures under polarized microscopy when compared with conventional. The first polar body is visible in both microscopes, but polarized microscopy can reveal telophase, interkinesis, and the real metaphase 2 oocytes. What is the difference between these stages? At telophase 1, the cytokinesis is not finished yet. And for example, if you would perform a polar body biopsy at this time, you would remove all of chromosomes because they are still not separated from the spindle. At telophase 1, the cytokinesis is not, After telophase, we should have an interphase in normal mitotic cycles. However, this is meiosis and a reduction of chromosomes takes place. Therefore, instead of interphase leading to chromosome duplication, we have a special phase called interkinesis. During this phase, the spindle disappears in human and is not detectable for about 2 hours. The disappearance of spindle is a normal spindle behavior during maturation of the oocytes and occurs before a new metaphase 2 spindle reappears. Therefore, it must be considered that the absence of spindle is not always a sign of pure oocytes. And finally, after interkinesis, we can reveal the real natural oocytes being at metaphase 2, which are arrested at this phase until fertilization. So let's go to summarize the phases of oocyte maturation as it is seen under polarized microscopy. And now I think that we should already understand the phases of meiosis. And we can go back to the former question, what is the correct time for ICSI? Before that, in order to specify it, we should know that the period of oocyte's ability to be fertilized and to create healthy embryos is not the same. Here is one example for understanding it. Maybe 20 years ago, we used to do so-called rescue ICSI in oocytes that failed to fertilize by conventional IVF. The result of this rescue ICSI was high fertilization rate, but no viable embryos or pregnancies, which means that the oocyte's ability to produce a healthy embryos is shorter than ability to be fertilized. Moreover, there is another very important factor influencing the correct ICSI timing. We have to distinguish between normal and delayed responders, because in delayed responders, the progression of meiosis is substantially longer as it is expressed in for example, in duration of anaphase, metaphase transition. Please keep it in mind because it's a crucial factor discussing later how to manage ICSI timing. So let's go to find out what is the real impact of ICSI in normal responders. Please note, there is no clear line between normal and delayed responders, but for our study, we consider the patients with more than 8 oocytes retrieved and more than 8% of them being at metaphase 2 as normal responders. We pull the oocytes from the same cohort and compare the effect of ICSI upon fertilization, blastocyst rate, and induction of abnormal development. In metaphase 2 oocytes, we wanted also find out if ICSI shift for 3-4 hours can influence the results. For the second group, we used telophase 1 oocytes with extruded first polar body, and for the third group, we used the oocytes at anaphase or early telophase, it means those with a visible signs of cytokinesis. Fertilization rate was unchanged in metaphase or late telophase oocytes, but it was significantly decreased in anaphase and early telophase oocytes. Even blastocyst rate was significantly impaired only in anaphase, early telophase oocytes. Moreover, we notice the presence of abnormal fertilization in this group of oocytes. Abnormal 2PN fertilization occurs when meiosis is not finished by extrusion of second polar body, but it proceeds directly to PN formation after interkinesis. Maternal PN was deployed as confirmed by PGT-A. This abnormal fertilization doesn't have to be distinguished from normal 2PN zygotes if you are not able to recognize a missing second polar body. Another anomaly induced by ICSI of immature oocytes is 1 p.m. fertilization. An extrapolar body extrusion was observed in 1 p.m. zygotes. What could be explanation of missing p.m.? Resulting embryos cleaved abnormally and were arrested very soon. Taken together, we can conclude that in order to avoid in vitro induced anomalies and keep high fertilization and blastocyst rate in normal responders, we have to keep these simple rules. And two oocytes having first polar body after OPU can be fertilized without any specific timing preferences. So-called M1 oocytes without first polar body at OPU should be fertilized at about 2 hours after the polar body extrusion. And the third one, use polarized microscopy if you can to verify the spindle or time-lapse recorded time of polar body extrusion. Now, you could ask me why so many words and pictures when the situation is rather simple and clear. Inject just the oocytes with first polar body. Yes, it's true, but only for normal responders, because majority of our